The Atlas detector is a general-purpose detector at the highest energy collider in the world, the Large Hadron Collider or LHC. It aims to identify the fundamental blocks that compose our cosmos and the origin of the universe itself. It processes a whopping 60 terabytes of data every second. And where does all this data come from? Well, there is something called a bunch crossing every 25 nanoseconds. That's millions of times faster than the blink of an eye. A bunch crossing occurs when a collection of protons collides with another, producing around 50 to 60 proton-proton collisions each time. This is already a lot, but in 2030 the LHC will undergo the high luminosity upgrade, increasing this number even further to 200. This is crucial for studying rare phenomena and hunting for signs of new physics. But how can we store so much data while running this experiment for years? Well, we can't. We need to choose which events we want to store, like snapshots of the interesting collisions. The trigger system filters the 40 million collisions per second to fewer than 3,000. First, with a hardware trigger, and second, with a software trigger, which is where my work fits in. Let's discover a bit more. The high luminosity upgrade poses a challenge. Our current computing infrastructure cannot handle the increased data volume, and this is where GPUs come in with their massively parallel architecture, being able to perform thousands of computations at the same time. What exactly am I doing? I'm working with one of the algorithms in the trigger, passing it to GPUs and optimizing it as much as possible. But before I can tell you what this algorithm is, we need to take a brief look into calorimeters and the standard model. Part of the Atlas detector is composed of calorimeters. They're made of dense materials to stop the particles from escaping so that we can measure their total energy. And they are divided into more than 180,000 cells to tell us where they deposited their energy. Imagine a camera but on a bigger scale. When we take a photo, each pixel records what it was seeing and where it was in the image. This is the standard model of particle physics. Our universe is governed by 4 forces, but let's focus on 2. The strong force affects the particles called quarks, and the electromagnetic force which allows us to lead our everyday activities like walking or charging our phones. The family of leptons also shows a familiar friend, the electron, and the elusive neutrino which almost never interacts. Now I can tell you about the algorithm I'm working on. In the calorimeter, neighboring cells with energy deposits are first merged into clusters. These clusters are then calibrated to ensure precise measurements, which is my focus. There are 3 main effects we need to correct for, but first we need to classify these clusters into electromagnetic or hadronic. They are electromagnetic if they come from particles like electrons or photons, or hadronic if they come from hadrons, which is 2 or more quarks held together by the strong force. Think of it like a molecule but for subatomic particles. This is important since we will apply different calibrations in each case. We start with the hadronic calibration. When hadrons interact with our calorimeter, we can't measure all their energy, like with their electromagnetic counterparts. They can lose energy via the strong force, which we cannot detect, and also produce neutrinos, which will just escape the detector never to be seen again. When the clusters are being created, some cells never get invited into the party and are just left outside of any cluster. Even though these cells were outcast by the cluster society, they may also contain important signal for our event, which needs to be accounted for. Finally, there is the dead material correction, and no, it has nothing to do with CSI or police investigations. In the middle of the calorimeter there is inactive material, where particles also leave their energy but we cannot measure it. This happens because the calorimeter modules also need physical support, as well as data acquisition systems. By parallelizing these algorithms using GPUs, we were able to obtain some preliminary results offering speedups of 22 times compared to using an ordinary CPU. Not everything works perfectly yet, but that is science, a process of continuous refinements, and every challenge brings us closer to unraveling the secrets of the universe.